All right. Welcome once again to the the Jam Chemistry syllabus lesson. We've been considering, we considered rather, atoms, molecules, and atomic structure. This is just a continuation from where we stopped the last time. In the last lesson, we delved into the concept of atoms, molecules, and ions, and we defined what an atom is. We also talked about the the atomic subparticles, or components of the atoms, and then of the atom, and then we basically um, talked about protons, neutrons, and electrons, and we gave definition and explanations to what they have. And we also looked at molecules. We defined what a molecule is. And we equally look at an ion and we define what it is. We categorize ion into cations, which are the positively charged ions, and then the anions, which are the negatively charged ions. Okay. After that, we also looked at some contributions that has been made by some scientists over the years, and we looked at people like Dalton, J.J. Thompson, Rutherford, R.A. Millikan, Mosley, and then Neil Ball. And so we looked at their contribution. And if you recall vividly, I told you that you should also go and read more about some of these the experiment that they conducted and their findings. Okay. We equally looked at atomic numbers and mass number to be precise, and we define what they are. Atomic number, we said is the same thing as or represent the number of protons in an atom's nucleus, and we said the mass number is the total number of protons and neutrons in an atom's nucleus, and we try to work out a little example, to work out if we are given the atomic number and mass number, how can we solve or look for the proton number, the electron, and then the neutrons in that particular atom? So I explained that in the previous lesson, and we now delved into electronic configuration, defining what electronic configuration is, and we also looked at the electronic configuration of the first 11 elements on the periodic table. And precisely, I gave you an example in writing the electronic configuration in orbitals, so the s orbitals, the p orbitals, and so on and so forth like that. So after that, I said you should write the electronic configuration for the for elements 12 to 20, and yes, some of you responded, which was very, very good. So please, if you have not, try and engage the question or the class activity and ensure that you drop it in the comment section when you've done that. Okay. We now looked at the rules for assigning electron into orbitals. We looked at the Pauli's exclusion principle. We stated what the Pauli's exclusion principle is. And we gave example to buttresses using hydrogen and helium. We also looked at the Hund's rule. We stated what the Hund's rule is, and then we also gave example to buttress the rule using nitrogen and oxygen. And we equally looked at the Aufbau's principle. We stated what the Aufbau's principle was, and we now looked at the order in which orbitals are being filled to 3s, 3p, 4s, and so on and so forth, based on the least energy. The one with the least energy will be filled first before it now progresses to the one with higher energies. Okay. After that, we looked at isotopy and mass number. We defined what an isotope is, and We use carbon-12 and carbon-14 as our example. You discover that they have the same number of protons, which is 6 protons, but their neutron number differs. Carbon-12 having 6 neutrons and carbon-14 having 8 neutrons. And we now worked in how to calculate relative atomic mass when you have you're dealing with 2 different isotopes with different percentage of abundance. Okay, so we did that. I showed how to do that calculation, very simple calculation. Okay, and I said you should try your hands on many others, as you see in past questions, in JAM past questions, that you can lay your hands on, following the same method. Okay. We also talked about the shapes of S and P orbitals. We said S orbital has what we call a spherical shape, is spherical in shape. The maximum number of electrons that it can hold is 2 electrons. And then we talked about the P orbitals being dumbbell shaped. And we said it is degenerated into Px, Py, and then Pz, that's for the P orbital. And then we said the maximum number of electrons that can be contained in the P orbital is 6 electrons. So each of the degenerates will have two electrons in them respectively. So we looked at that, and we now consider the periodic table. I told you that the periodic table is just an organization of elements in accordance to their increasing atomic number. So starting from hydrogen upwards to the one that has the highest atomic number, which are the actinides, So after that, we now looked at the periodic table in detail, looking at the families of elements on the periodic table. We considered the group 1 elements, which we call the alkali metals. We looked at the group 2 element, which is the alkaline earth metals. And then we looked at the constituents, as in the members of the group and their properties and characteristics. We also looked at the transition metals, the group 3 to 12 elements, and we also looked at some of their qualities or properties, as the case may be. Then we look at the post-transition metals. We describe what the post-transition metals are. We looked at the metalloids and then the non-metals, and then considered the halogen family. We explained what they are and their characteristics. Also looked at the noble gases, the group that has the inert elements, very unreactive. They are okay the way they are and all that. So we described them, and then I told you that you should do more work if you want more knowledge on reading up on lanthanide and actinide, although this is not really within your purview, so to speak. JAM may not really extend questions to those areas, but at least for information's sake, you can just, I told you that you should read up and try to get more understanding about it if you want to. But you can just focus on the first from group 1 down to the noble elements in group 18. So that's still fine, and it's still permitted under your JAM or within your JAM syllabus. Okay. So we looked at the trends on the periodic table. We talked about ionization energy. Ionization energy, we said, increases across the period and decreases down the group. We looked at the ionic radii. We described the trend also across the period and down the group. We also talked about the electronegativity, having this almost similar trend also with ionization, in the sense that it increases across the period and decreases down the group. Talked about the electron affinity, and this was where we stopped in the last lesson. So we're going to continue today with chemical bonding, and we refer chemical bonding refers to the attractive forces that hold atoms or ions together in molecules, in compounds, or crystalline structure. So that is what we call the that's what we refer to as chemical bonding. So we said these forces are the result of interaction between the electrons of atoms, and they play a crucial role in determining the properties of substances, including their physical, chemical, and mechanical characteristics. So we want to look at types of chemical bonding that we have. And the first one we are considering is electrovalent bonding or ionic bonding. Now, electrovalent or ionic bonding occurs when electrons are transferred from one atom to another, resulting in the formation of oppositely charged ions. Now, this transfer occurs because atoms tend to lose or gain electron in order to achieve a stable electron configuration, typically to that of the nearest noble gases. So we've actually talked about this in the previous class. We said most times atoms are willing to give off electron just to attain, the noble gas configuration, and they are also willing to take on electrons to themselves to be able to, have a stable noble gas configuration. So basically, electrovalent bonding or ionic bonding is talking about a bond that exists between a metal most of the time and a non-metal, And what happens is that there's always a transfer of electron, direct transfer of electron from the metal to the non-metal. So a typical example is what we have on the screen. The right-hand side of the screen, you have sodium combining with chlorine. Sodium has an atomic number of 11, and that's the distribution of electrons. And when you look at it closely, you discover that it has one extra floating electron in its outermost shell, or the valence shell, which is really more than willing to give off, to take it off completely. If you look at that of chlorine, you discover that it has 7 electrons in its valence shell. So it's willing to take on one more electron to attain the octet configuration, that is having 8 electrons in its outermost shell. So what happens is that now sodium gives off one of its electron in the valence shell, and then gives it up to chlorine. So they both attain a stable configuration, and by so doing, the compound sodium chloride is formed. So there's a direct transfer, of electron, complete transfer of electron. But this is not the case with the second type of chemical bonding, which we call covalent bonding. In covalent bonding, what happens basically is that there's a sharing of electron. Electrons are shared, instead of transferring, there's a sharing. So I bring mine, you bring yours, we share together, and then we are all okay. And that is what happens with covalent bonding. So what happens basically is that, take for instance, let's use water as an example. Oxygen will share electrons with 2 hydrogen atoms, and then the oxygen atom, which has 6 valence electrons, shares 1 electron with each hydrogen atom, which has 1 valence electron, forming a covalent bond. Let's look at this diagrammatically. Now, if you look at this, now you discover that hydrogen has just 1 valence electron, as we can see here, and that's formation of H2O now. So you have 2 atoms of hydrogen coming together with 1 atom of oxygen. Now oxygen has about I think about 6 valence electron. That's the number of electrons in its outermost shell. There are 6. So what it does is that, okay, I share my electron with you. You will become paired up like that, and when we become paired up, we'll end up having hydrogen end up having a duplet configuration, which is like that of which is similar to the electronic configuration for helium, so it's stable. Oxygen end up having what's it called, 8 electrons in its outermost shell, which is similar to that of neon, a noble gas, which is also stable, because it's octets, you understand. So that is what happens with covalent bonding. There's a sharing, that we see, existing with covalent bonding. Okay. All right. Now the next thing that we need to look at is hydrogen bonding. Now, hydrogen bonding is a typical or a special type of electrovalent bond that occurs when hydrogen atom covalently bonded to a highly electronegative atom, like oxygen, nitrogen, fluorine, chlorine, and so on. So it's attracted to another electronegative atom in a nearby molecule. So basically what happens is that in a molecule with a highly electronegative atom, such as oxygen in water, the electron pair is pulled closer to the electronegative atom. So it leaves the hydrogen atom partially, positively charged, and this positive charge can attract the lone pair of electrons from another electronegative happen, and that is what happens basically with hydrogen bond, and we can see this typically in water, it exists in water. And not only that, hydrogen bonding has some importance because it plays a crucial role in biological systems, such as the structure of DNA and protein folding, and it contributes to the physical properties of water. And water is very, very essential to life, and to our existence as human, and even to animals and the world in general. So these are some of the importance of hydrogen bond or bonding. If you look at it, just like we were talking about, you have a net partially positive charge that is created here, then it's now bonding with oxygen that way. So it's able to attract the electronegative atom to itself. Then so an hydrogen bond is formed as a result of that. Okay. So the next one is metallic bonding. Now, metallic bonding occurs between metal atoms where electrons are not shared or transferred between individual atoms, but instead form a sea of delocalized electrons that move freely, around positively charged metal ions. Now, this type of bonding explains many of the physical properties of metals, such as electrical conductivity and their malleability also. So what happens basically in metallic bonding is that the atom release some of their electrons into a common pool of delocalized electrons, which are free to move through the metal lattice, So the metal cation, which is positively charged, are held together by the electrostatic attraction to the delocalized electron. A very good example is in a piece of copper. The copper atom releases their valence electron to form a sea of electrons that can move freely, allowing copper to conduct electricity. This metallic bonding gives copper its high electrical conductivity. So that is what metallic bonding is all about. You discover that the metal will release some of the electrons into a common pool of delocalized electron, and it gives them freedom to be able to to move freely. The electrons are able to move freely, and then it also enhances the conductivity of metals, electrical conductivity of metals, and all that. Some of the properties of metallic bondings are they are usually good conductors of electricity and also heat. They are malleable, that is, they can be hammered into thin sheets, and they are ductile, they can be drawn into wires, and due to the flexibility of the electricity, so they are ductile, you can draw them into wire. Okay, so that's those are some of the properties of metallic bonding. The next one we need to look at is the coordinate bond or the dative covalent bond. We call it coordinate bond or the dative covalent bond. So a coordinate bond, also called a dative covalent bond, is a type of covalent bond where both electrons in the shared pair come from the same atom. This type of bond is commonly found in coordination complexes where a central metal atom or ion is surrounded by ligands, and that's what you have in a coordinate bond or dative covalent bond. Mind you, the sharing pair or the sharing of electron is most of the time is supplied by and a particular atom, compared to covalent bond whereby you bring yours, I'll bring mine, and all that. But it is not really like that with coordinate or dative covalent bond. So the mechanism basically behind dative covalent bond or coordinate bond is that one atom donates a lone pair of electron to another atom that does not have an electron to share. Now, this forms bond where both electrons come from the donor atom. So this is what we will find out in dative covalent bond or coordinate bond. Now, an example is in the complex FeCN6. That's the iron, which is F3 plus, forms coordinate bonds with 6 cyanide ions, and that is what happens now. The cyanide ion each donates one lone pair of electrons to the central ion atom, forming a stable complex. It forms a stable complex. You can also find them in other complexes, apart from the ferrocyanate complex. We can also find them in copper. We can find them in when when silver and nitrogen come together to form a complex. So we can also see similarity whereby two ammonium molecules donate lone pair to the silver ion, forming the coordinate bond. Okay. So the next one that we need to look at is please, if you have any question, please feel free to drop them in the comment section. If you need clarification, please also point my attention to it by dropping in the comment section so that I can react to it, accordingly. Okay, so we also have the van der Waals force. The van der Waals force is another form of chemical bond, albeit a weak chemical bond, but it's another form of chemical bond that we'll be considering soon. So the van der Waals forces are weak, non-covalent interactions between molecules or atoms. These forces are responsible for the condensation of gases into liquids and the formation of solid molecular compounds. Now, there are three types of van der Waals forces. The first one is called the dispersion forces. The dispersion forces is also referred to as the London forces. Now, these are the weakest type of van der Waals forces and arise from temporary fluctuation in the electron distribution around atoms, creating instantaneous dipoles that attract neighboring molecules. Example, dispersion forces are significant in noble gases like helium, where the weak interactions between the atom leads to condensation at very low temperature. So that's an example where we can find the London forces or the dispersion forces. The second type of van der Waals force is what we refer to as the dipole forces. Now, this occurs between molecules that have permanent dipoles, that is positive and negative ends. And the positive end of one molecule is attracted to the negative end of another molecule. An example is in hydrogen chloride. The positive hydrogen end of one molecule is attracted to the negative chlorine end of another molecule. So this is an example of a dipole forces. The other type of van der Waals force is hydrogen bonding. And for this one, this is a type of dipole interaction, as discussed earlier. And it occurs when hydrogen is covalently bonded to a highly electronegative atom like oxygen or nitrogen, as the case may be. So these are some of the chemical bonding that we have, in chemistry. And I hope you got them all. So we have been able to talk about the electrovalent bonding, the covalent bonding. We've talked about the hydrogen bonding. We've also equally looked at the metallic bonding, and then the coordinate bond or the dative covalent bond. So that's what we have been able to look at in this particular lesson. Now, I just want to summarize quickly that this lesson introduced the fundamental concept of atoms, molecules and an ion, emphasizing the atomic structure and subatomic particles, the protons, the neutrons, and electrons. The lesson also explored the electronic configuration rules, talking about the Hofbau's, the Hund's rule, and then the Pauli's exclusion principle. And it also talked about the nature of isotope and then the classification of elements in the periodic table. Students also examined various, and we also examined the various chemical bonds, including ionic, covalent, metallic, hydrogen, coordinate bond, and van der Waals forces, as well as periodic trends like ionization energy and how they trend on the periodic table, electronegativity, and then the atomic radius. These were some of the things that we were able to cover in the course of this lesson. So please, if peradventure you did not get any concept clearly, or you need more explanation on a particular aspect of the topic that we've just considered, kindly put them in the comment section, and then I will react to it accordingly. Okay. Now let's quickly evaluate the lesson that we've had with these few questions. So the first one says that which subatomic particle is negatively charged? You have the options there, so you can just put what you feel is the right answer in the comment section. and I'll give a thumbs up if it is correct. And if it is not correct, I'll give a thumbs down, showing that it's not correct. So the subatomic particle, we've talked about it. So we said which subatomic particle is negatively charged. Okay. We said what defines the atomic number of an element? What defines the atomic number of an element? Is it the number of neutrons? Is it the mass number? Is it the number of protons or the number of electrons? So put your answer in the comment section, and then I will react accordingly. Now, which orbital shell is spherical? We've talked about this when we're talking about the s and the p orbital. So please look through the options and let me know what's the right answer is. Question 4 says that which rule states that no two electrons can have the same 4 quantum numbers? So recall the rules that we considered: Pauli's Pauli exclusion principle, Aufbau's principle, and then the Hans rule, and tell me which one you feel is the right answer to this question. Okay. We equally looked at question around chemical bonding, and this question says that in which type of bonds are electrons shared? So you tell me, pick the right answer, and then you share in the comment section. Which of the following elements is an alkali metal? We've talked about this when we're talking about when we're discussing the families of the periodic tables on the periodic table. So look at the options that we have there. Is it calcium? Is it iron? Is it sodium or neon? And tell me which one is among them is the alkali metal. This also question talks about chemical bonding too. Excuse me, please. So it said, what type of force exists between hydrogen and chlorine molecules? So look at the option and let me know what you feel the right answer is, and then which group contains the least reactive elements. So you have the options there. You can just react to it accordingly in the comment section. All right, I want to say a big thank you for joining me in this lesson today. And I hope you benefited a great deal from the lesson. And I will see you in the next class. The next class we are going to be looking at nuclear chemistry. Is also an aspect of is a component of the chemistry syllabus for JAM. So we are going to be looking at nuclear chemistry in our next lesson. So thank you for watching and listening. I'll see you in the next class.